So welcome back to the LTE interface training. Now let's talk about the uplink LTE physical channels. We have three different kind of channels in the uplink. First is the physical random access channel. Second is a physical uplink shared channel. And last but not least, the physical uplink control channel. So let's start with the random access channel. So the random access channel, here we see the structure of this channel. It starts with a cyclic prefix, like for normal OFDMA transmission, followed by the symbols, and they represent a sequence which can distinguish different mobiles which try to get access to the cell. And then after the sequence we have a guard period which has different widths, so different lengths, depending on the scenarios which are supported. So the guard period is one of the important factors of the physical random access channel configuration. So it depends on the delay we have on the interface. So the first user equipment A is very near to the receive antenna. So there is a low delay, almost no delay can be found. So the user equipment synchronizes in the downlink and takes the downlink synchronization for the uplink, because before we have sent the random access channel, we have no uplink synchronization. So here we see no gap between the transmission of some other users maybe in the uplink, and then we see the starting position of the subframe, starting with a cyclic prefix, and then we have the sequence, and then the guard period. And after this, we have the transmission on another subframe. If we go further away, this is user equipment B. So we have a delay. So this means our sequence arrives somehow later. And so we need the gap so that we have no overlapping between the random access and the subframe which is used by some other users. So the guard band length depends also on the cell radius. So it's the main factor which defines the cell radius. We have different configurations which are supported by the random access, which is suitable for different scenarios. So the preamble formats are named 0 up to 4, whereas the format 4 is only used for TDD. So we have in FDD formats 0 to 3. And they are defined by the sequence length given in the time frame of TS, and the CP, which is a cyclic prefix given in TS and in microseconds, and then the guard time given in TS and also in microseconds. And then the maximum delay spread is directly correlated to the length of the cyclic prefix. So you see the higher cyclic prefix, for example, format 1 has a higher cyclic prefix than format 0. So it's more suitable for larger cells. And the delay spread supported is then 16.66 microseconds compared to 5 microseconds for format 0. And the guard time, the lowest guard time we have is 100 microseconds. This is equivalent to a cell radius of 14.5 kilometer. And the largest configuration is format number 3, which supports a cell radius up to 100 kilometer. Representation of the different random access formats in the time frequency domain is shown here for the FDD versions. So the format 0 has the smallest size. It fits into one subframe, so it's less resource consuming. So it is preferred for most LTE cells. So we have to restrict then the cell radius to 14.5 kilometer because the introduced guard period is very small. But then you see format number 1 has a much longer cyclic prefix and uses the same symbol length as the format 0, but it doesn't fit in just one system subframe, but it needs 2 subframes with a longer gap guard period. So it's suitable for larger cells and for high delay spreads. And then format 2 has a long symbol length but a small cyclic prefix, but it also fits into 2 subframes, but the guard time is much smaller, so the cell radius is smaller than for format 1. And the longest random access is the format number 3, using a large cyclic prefix and a large symbol length. And it doesn't fit in 2 subframes, but it needs 3 subframes. So the location of the physical random access channel in the resource grid, in the frequency domain, it is defined by a frequency offset. So the offset is typically not 0, starting from the lowest frequency, because in this case it would overlap with control signaling. So there is always an offset, and there's also some optimization feature which changes the offset depending on the control channel load. So, and here we see the configuration with format 0. So it fits in one subframe, and it consists of 839 subcarriers. So the sequence length of the random access channel has 839 symbols, and in this sequence is coded a preamble. So every cell has 64 different preambles, which are sent on 839 subcarriers with a subcarrier spacing of 1.25 kilohertz, which is much lower than the frequency spacing we use for the normal transmission. So this is the configuration in the frequency domain. In the time domain, we use the physical random access configuration index, which is shown here. The index runs from 0 to 63. Only part of it is shown in on this slide, starting with configuration 0. You see every configuration maps to one special format. So the smaller numbers correspond to the small formats, like format 0 is the smallest format. And it means that the random access can occur only in the even system frames. So in system frame 0, 2, 4, and so on. And the configuration index also defines the subframe in the system frame which can be used for the random access. So we have only one subframe where the random access can be sent. This is subframe number 1. And if we go to higher indices, then we get more opportunities to send the physical random access channel, like, for example, on index 3, we can send random access in every system frame. And then later on, we can send the random access several times per system frame. So if we need more capacity for the physical random access channel, then we have to increase the configuration index. The configuration of the physical random access channel is transmitted in the system information type 1, so including the root sequence index, which is running from 0 to 839. And from the root sequence index, the user equipment derives the preambles which can be used in this specific cell. So we need to plan the root sequence index. So neighboring cells should use different root sequence indices so that there can be no confusion of the random access channel between neighboring cells. Then we have the configuration index, which we have discussed in the last slide. Then we have the high-speed flag. So from the root sequence index, we generate the 64 preambles, but this can only be done for small cell radius and for low mobility. In case of larger cell radius and higher mobility, one root sequence index cannot produce 64 preambles, but less. So if we are in a high-speed cell, we have a restriction on the preambles, so then we need more root sequence indices per cell. So this has to be taken into account in planning of the root sequence index. Then we have the zero correlation zone, which is related to how many preambles can be generated from one root sequence index. And then we have the frequency offset, which is defining the distance between the lowest frequency of the physical random access channel and the lowest frequency of the LTE carrier. So the next channel, so the last channel in the uplink is the physical uplink shared channel. And the resource grid is similar to the downlink, but we have no control region at the beginning in the first symbols, in the first up to 3 symbols. But all these resource elements can be used by the user data, starting from the lower frequencies and going to the higher frequencies. In between, in the middle of the first time slot, this symbol is used for the reference signal. So the reference signal is repeated after another 0.5 milliseconds. So we have 2 reference signals included in one uplink transmission. And the sequence length of the reference signal depends on the bandwidth of the allocated resources. So the uplink shared channel transmits control plane data as well as user plane data. And it transmits also layer 2 data, uplink data. This is the uplink control information. And the uplink control information consists of channel state information, which is mainly CQI, channel quality indicator, as well as the rank indicator, which is telling us something about the quality of the link, of the downlink. And then another information, uplink control information, is the HARC feedback, which is just an ACNAC feedback about the downlink transmission. If the user uses the uplink shared channel, he cannot use the uplink control channel, so he has to map the uplink control information into the uplink shared channel. So the mapping is done like what is shown here. the HARC feedback is sent directly near the reference signal. So these resource elements have the best demodulation performance. Then farther away from the reference signals are sent the rank indicators. And on top, at the lower frequencies, are sent the channel quality indicators. So the last uplink channel is the uplink control channel. This is transmitted at both edges of the frequency carrier. So in the minimum configuration, one resource block is used by the uplink control channel, and this channel is hopping. So we have an inter-time slot hopping of this channel. So this is used, the hopping is used to have frequency, maximum frequency diversity. If the uplink control information amount is increasing, so there are many users which have to send feedback in the uplink, then another resource block can be used for the uplink control channel, and so on. Maybe several, up to 6 or 10 resource blocks can be used by the uplink control channel. Thank you for watching.